Algebra 2. Let's open up and work on chapter 4. We are in section 1. We're going to start graphing exponential growth functions. Our chapter is on exponential and logarithmic functions, which I think is a ton of fun, and I hope you agree. So let's warm up. Evaluate the expression without using the calculator. So we need to remember our exponential rules. When we have anything negative, that means we want to make it positive and put it in the denominator. And then we can go ahead and square the 5 and get 25. This one's a little bit more difficult, but I need to remember everything. So this is sort of like square times 1/3 is the same as 2/3, right? Well, I can take the cubed root of 8 pretty easily. And that too can stay out there, or it can be out here. I'm going to move it out there because that makes better sense to me. Cubed root of 8 is 2, and 2 squared is 4. I know you can use a calculator on that one and get the same answer, but knowing how everything works, knowing what a fraction means is really important. So evaluate their expression without using a calculator. Let's look at this thing first. That means that I'm a second root of 4, a square root of 4, because that's that right there. And then I want to cube it, and then multiply it by -3. So square root of 4 is 2 to the 3rd power is 8. And that gives me -24. I got an Apple Pen for Christmas. Can you tell my handwriting's a little bit better? I'm pretty excited. Number 4, state the domain and range of the function. Remember, we could graph this and figure that out. Because if we look at the graph, the domain is our x values and the range are our y values. The domain is our input and the range is our output. So on this particular one, I'm not taking the square root of anything, so the domain, which is our x value, would be in fact all real numbers. But what's crazy is our range. If I look at this right here, no matter what I put in for my x value, I'm going to have a negative there. And then I'm going to add 3 to it. So the smallest this could be right here would be 0. And then it's going to go negative. So I guess that'd be the biggest it could be is 0. And then it's going to go negative. So I'm going to have any negative number and add 3 to it. So that means that the biggest y could ever be is if this was 0, and y has to be less than or equal to 3. Okay, you could always graph that and just see where it affects the y-axis, and that would work well. All right, let's talk through our new concepts. An exponential function has the form y equals a times b to the x. Notice our variable is in the exponential spot. A cannot equal 0, and the base b is a positive number other than 1. If a is greater than 0 and b is greater than 1, then the function y equals a b to the x is an exponential growth function. This means that it's growing. It's getting bigger. That's an exponential growth function, and b is called your growth factor. The simplest type of exponential growth function has the form y equals b to the x, where a would be equal to 1, and we just ignore it. Moving on, the parent function for exponential growth functions. The function f of x equals b to the x, where b is greater than 1 is growth function with a base b. The general shape of the graph of f of x equals b to the x is shown below. Okay, let's see. These right here are the 2 points that are important. Okay, 0, 1 and 1, b. But let's look here. the x-axis is an asymptote. We're never going to cross the x-axis. That's what an asymptote is. We aren't going to go into the negative. We aren't going to go down here at all. An asymptote is a line that a graph approaches more and more closely but never crosses. The graph rises from left to right, passing through the points 0, 1 and 1b because it's a growth, right? So the domain of all these is all real numbers, and the range is positive numbers, never 0. Okay, so graph y equals 2 to the x. The first thing we're going to do is make a table of values. I just picked values. I picked small ones. This is an easy one because we're 2 to the x. If I plug in -2 for x, that means that it's going to be 1 over 2 squared, which is 1 over 4. -1 would give me 1 over 2. Anything raised to the 0 power is 1. That's a rule we learned a long time ago. 2 raised to the first power is 2. 2 raised to the second power is 4. 2 raised to the third power is 8. And then this is already graphed for you. Notice these right here are 0, 1 and 1, b. It's a really easy way to get your curve shape, right? The graph of a function y equals a b to the x, notice we have an a again, is a vertical stretch or shrink of the graph y equals b to the x. Depending on what a is, it's a vertical stretch or shrink. And we'll get to that, right? The y-intercept of the graph y equals a b to the x occurs at 0, a rather than 0, 1. So that right there is important. Let's try one. This right here is multiplication. I couldn't get my multiplication dot to work really well, so I had to use a star. I hope that's all right. So with these, we are actually going to plot just our points of, I don't know what to call them, our points. Okay, we talked about the first one being 0, a, right? And the second one being 1, b. What's interesting here, though, is our b value. So our point is going to be 0, 1/2, and 1, 1/2 of 4 is, in fact, 2. Okay, so we plot those 2 points, and then we can somewhat easily draw a curve, making sure we hit those 2 points, which gives us enough information for a curve. Okay, let's try another one. Now, if you remember, this right here, okay, reflects over the x-axis, right? That just turns it upside down, okay? So I'm going to plot here. Our a value is actually going to be -1 times 5/2 to the x. That's why I'm going to graph 0, -1, because that is 0. Oh, sorry. That is actually 0, a. And then I'm going to graph 1, a times b, which is -5/2. So we've got those 2 points, and that's enough information to graph a curve, knowing that our curve is going to be under the x-axis. Okay, knowing that here my domain is actually all real numbers, but my range is going to be y is less than 0. Okay, that x-axis is still an asymptote. We're not going to cross the x-axis. All right, now things get just a tad bit more difficult. We're going to talk about translations. To graph a function in the form y equals, all right, a little bit bigger, a times b to the x, not just x now, it's x minus h in the exponential spot plus k. That means that our h is going to be a horizontal, we call it a slide, translation. The slang word for that would be a slide. So horizontal translation, or just a plain old slide. And the K is a vertical. You guys are probably hearing more clicking noises with my new pen. Sorry. And translation, again, is just a slide. Point out, though, it's x minus h, so h would be my horizontal left and right, and then k would be my vertical up and down, but that would be a plus in front of the k and a minus in front of the h. Okay, so let's mess with it a little bit. Graph this, state the domain and range. First, we would begin by graphing just the basic y equals 4 times 2 to the x, where the points that I'm interested in are 0, 4 and 1, 8. And if you'll see, I'll graph that in red, blue, 0, 4 and 1, 8. Then we actually want to take that and translate it. I don't know why I'm still in highlighter, sorry. My h value, it's x minus h, is x minus 1. So my h value is 1. That means I'm going to go write 1 value. And then right here, I have minus 3. So k is a negative 3, so I'm going down 3. So let's move to red. That means I start at my 0, 4. I move right 1, and then down 1, 2, 3, and put a new dot. Up here, I start at my 1, 8. I move right 1, I go down 1, 2, 3, and I put a dot. And my translated, or my slid curve is as shown. Okay, I know we said the x-axis is an asymptote, but our asymptote has now moved to right there. Our new asymptote is actually, let me get my pen out, is actually not the x-axis anymore. It's the y equals negative 3 axis. Therefore, our range, y has to be greater than negative 3, and our domain is all real numbers. I can input anything into that equation, but the domain I get out is greater than negative 3. Okay, guided practice. Graph the function, state the domain and range. Here, I'm going to plot a few points. This is y equals 1 times 4 to the x. So my points are going to be 0, 1 and 1, 4. I graph those 2 points, 0, 1 and 1, 1, 2, 3, 4, and then I graph. My domain is all real numbers, fancy R. My range is y is greater than 0. Here, I'm going to graph my 2 points, 0, 1 half and 1, 3 halves. So 0, 1 half is there, 1, 3 halves. Draw your curve, domain, all real numbers, range, y is greater than 0. Ooh, now we're moving. So first I'm going to graph y equals 1 times 3 to the x. And I'm going to graph that at 0, 1 and 1, 3. Sorry, 0, 1. Let's see. I'll do that in red. 0, 1. And hold on a second. I couldn't see my graph. And say 1, 1, 2, 3. Now how am I going to move this? I have x minus 1, or x plus 1 is my slide, but that should be x minus a negative 1, because that's the form. So I'm going to go left 1 value, and then my k value, this is h, my k value is 2, so I'm going to go up 2. So from that point, let's get a blue pen out. I'm going to go left 1 and up 1, 2 and put a dot. Left 1, up 1, 2 and put a dot. So my curve looks like that. Cool, we did it. So my domain is going to be all real numbers, and my range is going to be y is greater than 2. All right, moving on. Exponential growth models. When a real-life quantity increases by a fixed % each year or other time period, the amount y of the quantity after t years can be modeled by the equation y equals a 1 plus r to the t, where a is the initial amount and r is the % increase expressed as a decimal. Note that the quantity 1 plus r is the growth factor. This right here is important. Okay, we're going to use that. So remember these, write them down, highlight them. Okay, we need them. For this example, in 1996, there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number of incidents increased by about 92% each year. That's a percentage. That's a number. Write an exponential growth model giving the number n of incidents t years after 1996. About how many incidents were there in 2003. So we've got a multi-part problem here. They want us to graph the model and then use the graph to estimate the year when there were about 125,000 computer security incidents. So in this, we know that the initial amount, which is A, in that equation we talked about, A is my initial amount, and that is 2,573. And the % increase in the problem, R equals 0.92. 92% goes to 0.92 as a number. So the exponential growth model is n equals a times 1 plus r to the t. My initial amount, 1.92, which is 1 plus r, to the t. T is my unknown. Okay, there we go. That is my exponential growth model. Now we're going to graph the model. Okay, they graphed it for us. Graph the model. Okay, that's harder when the numbers are bigger. Okay, I can help you, take your time, etc. So using this model, you can estimate the number of incidents in 2003. So we know in 2003, T is 7, 96, 97, 98, 99, 1000, 2000, 2001, 2002, 2003, 7 years. Just had to count that one out. So put that into our growth model. 2573, 1.92 raised to the 7 is approximately 247,485. Cool. Now, we can look at this. Our graph passes through approximately that number, hits the curve that we graphed, we go down, and that is 2006. The graph passes through the points draw a smooth curve, but we're going to use that curve to estimate that t is about 6, which is 2002. Oh, I'm sorry, I'm still in highlighter. So the second part of that question where it said estimate the number of incidents in 2002, that's t equals 6. So the amount of incidents, I had to go back and reread the question, I'm sorry, is approximately 125,000. All right, so in example 4, estimate the year in which there were about 250,000 computer security incidents. So I'm going to the graph. 250,000, go over, hit the curve, go straight down. That is 7, but it's 7 years since 96. So 1996 plus 7 is actually year 2003. Cool? Cool. All right, guided practice. So in the exponential growth model given, identify the initial amount, the growth factor, and the percent increase. Okay, initial amount. Growth factor is 1 plus r equals 1.39. Therefore, r equals, oh, sorry, that is my growth factor. Scratch that. Growth factor is growth factor is 1.39, and the percent increase is that 1 plus r equals 1.39. Therefore, r equals 0.39, which equals 39%. All right, last example. So compound interest. Love compound interest. So much fun. Exponential growth functions are used in real-life situations involving compound interest. Compound interest is interest paid on the initial investment called the principal, P, and on previously earned interest. Interest paid only on the principal is called simple interest. Okay, we have compound interest and simple interest. All right, so for compound interest, consider the initial principal P, that's our variable, deposited in an account that pays interest at an annual rate R, represented as a decimal, not a percentage, compounded n times per year. The amount A in the account after t years is given by this equation. So this is the equation that we use in many different ways, okay? Okay, so let's try an example. You deposit $4,000 in an account that pays 2.92% annual interest. Find the balance after 1 year if the interest is compounded with a given frequency. So this is my initial amount, 2.92% annual interest, and find the balance after 1 year if the interest is compounded with a given frequency. So quarterly, that means I'm compounding 4 times a year. Daily means I'm compounding 365 times a year. So let's go ahead and use our our equation. A equals P, 1 plus R over N to the T, where P is 4,000, R is 0.0292, N for part A is 4, and T is 1. Plug it all in. 1 plus 0.0292 over 4 raised to the 4 times 1. That's there. Ran out of space. You do all the math on this, and you've got an answer of $4,118.09. Okay? Dollars. Okay, when you're compounding daily, same equation. Principal, 1 plus 0.0292 over 365 raised to the 365 times 1 year. T is 1. Okay, crunch some numbers, and you get a pretty close number, right? Hold on. Yeah, first answer was $4,118.09. Second answer is $4,118.52. Huh, interesting. Cool. Oh, okay, we already did that one. All right, let's try another example. So I've got $2,000 deposit. That's my initial amount, an account that pays 4% interest rate. So move the decimal 2 places. Find the balance after 3 years if the interest is compounded daily. So 365, and then 365 times 3. Crunch those numbers, you get $2,254.98. We made it! Daily homework quiz. Like I've done before, I left the answers in here. They're great practice problems, but you also have homework assigned. So go ahead and look at these or print them out. There's another. And another. That's actually the last one. Great work today. Super duper proud of you. See you later.